Thank you very much. Pleasure to be here. Let me just share my screen. Is it okay now? Can you see it? Okay. And without further ado, so the title of this talk is, as Selron mentioned, Continuous versus Discrete Optimization of Deep Neural Networks. This is a joint work with my student, Omer Kabetz, and it appeared in the last NeurEPS's Spotlight. So let's start with a little bit of motivation. It's widely accepted that the success of deep learning, deep neural networks, is largely driven by the optimization algorithms that people use, which in one way or another are variants of gradient descent. And if you want to theoretically analyze these phenomena, then roughly speaking, there are two classes of approaches. One is to analyze a continuous version of the optimizer, continuous version of gradient descent, which is gradient flow. It's what you see here. It's a continuous curve in space that moves in the direction opposite to the gradient. And the other approach is to directly analyze gradient descent. Now, the advantage of analyzing the continuous algorithm, gradient flow, is that it is easier to do so. You have a lot of mathematical machinery at your disposal, continuous mathematics. The downside is that it's unrealistic. Okay, these are not the algorithms that one really runs in practice, and in particular, there's no notion of computational efficiency. And the extent to which gradient flow over deep neural networks really represents gradient descent is currently an open question. And this is the question that we sought out to address in this work. And before giving our results, let me just give a really brief background in numerical integration. This is going to be something that we're going to rely on. So in numerical integration, you start off with a differential equation that you would like to solve. Okay, so you have this curve in space, whose movement is determined by this vector field. The velocity at any point determines the movement. And oftentimes solving the differential equation and obtaining the solution exactly is impossible. So what people do is numerically approximate it. And a very, very common approximation method is known as Euler's method. And the idea there is that you try to approximate the solution in time steps with eta time in between. Eta is the step size. It is predetermined. And the way that you attain the k+1 estimate is by taking the kth estimate and adding to it a small movement in the direction of the vector field. And so the movement is scaled by the step size. And so this is Euler's method. It's perhaps the most basic numerical integrator. And there are various results bounding the approximation error of Euler's method. From our perspective, a very interesting result is as follows. It's called the fundamental theorem. It's a relatively recent result from late 20th century. And what it says is the following. The distance between the true solution at time t and the corresponding iterate of the numerical approximator is upper bounded by eta times t times exponent. And the exponent is of an integral. And what you integrate is the maximal eigenvalue of the Jacobian of the vector field. So let me repeat this. I have my solution theta. And at every point along this curve, there is the vector field g. I can take the Jacobian of g, take the maximal eigenvalue, and I integrate this thing. And then I exponentiate, and this is my bound. How is this relevant to us? It turns out that numerical integration is very closely related to optimization. Okay, so numerical integration, we had this vector field. In the case of optimization, there's some function f that we want to minimize. And we define a vector field to be minus the gradient of this objective function. And now the differential equation just boils down to gradient flow. And Euler's method is no other than gradient descent. And the result on the numerical error of Euler's method gives us a bound on the distance between gradient flow and gradient descent. And the bound says that the distance between gradient flow at time t and the corresponding iteration of gradient descent is upper bounded by the step size eta times t times exponent. And now the exponent is over minus the integral of the minimal eigenvalue of the Hessian along the gradient flow curve. Okay, so the distance is proportional to exponent of minus the integral of the minimal eigenvalue of the Hessian along the gradient flow curve. And this result is going to underlie our analysis. And so before we get into deep neural networks, let's try and get some feel of what this result means. First thing to notice is that if I want the distance between gradient flow and gradient at time t and gradient descent to be no bigger than epsilon, I can choose a step size that will ensure it. However, the step size might need to be very small. And now it's the question of how small does it need to be? So to gain some intuition, we replace this upper bound by something that's looser. Instead of taking the integral of the minimal eigenvalue of the Hessian along the gradient flow trajectory, we take the minimal eigenvalue of the Hessian across space. So it can only be smaller. Therefore, the right-hand side here will only grow. And the bound that you get depends now on the convexity of the objective function. If the objective is strongly convex, minimal eigenvalue of the Hessian across space is positive. And you get that the step size needs to be on the order of epsilon, doesn't even depend on t, and you're good. So over a strongly convex function, gradient flow and gradient descent are close to one another. You don't need a very small step size. If your objective is non-strongly convex, then the minimal eigenvalue of the Hessian is 0 across space. And now the step size, eta, needs to behave like epsilon over t. So the longer you want gradient descent to follow gradient flow, the smaller the step size needs to be. But it decays pretty gracefully. It doesn't have to be super small. In the case of a non-convex objective, now the step size needs to be exponentially small in t. So if it's not exponentially small, the bound that we have will not hold. And this is a problem, right? It seems that in order for a gradient flow and gradient descent to be close to one another, step size needs to be exponentially small. Now, one may ask whether this is an artifact of our analysis, but it turns out that this bound is tight. Okay, there exist settings with a non-convex objective where if the step size is not exponentially small, gradient flow and gradient descent will immediately diverge from one another. Okay? So we're in a bit of a pickle. We see that in the worst case, gradient flow and gradient descent have nothing to do with each other. And now there's a question of what's happening with deep neural networks. So fortunately, in the case of deep neural networks, even though the objective is non-convex, specifically over trajectories of gradient flow, it's roughly convex. To be a bit more specific, the minimal eigenvalue of the Hessian along gradient flow trajectories, if these trajectories start near the origin, and the optimized objective is that of a deep neural network with homogeneous activation, this ReLU, leaky ReLU, or linear, then the minimal eigenvalue of the Hessian is only going to be slightly negative. It's not going to be too negative. And it actually kind of converges to 0 as the optimization progresses. So in light of the general theorem that we saw, this suggests that over deep neural networks, gradient flow is similar to gradient descent. And this is some special property of deep neural networks. And so to demonstrate this, we show how a continuous analysis can be translated to a discrete result. We look at the setting of a linear deep neural network, could be arbitrarily deep, has a scalar output, and we analyze gradient flow over this model, and we show that it converges to global minimum almost surely under random near 0 initialization. That means with probability 1 under an initialization that's near 0. And if you feed this into the generic gradient flow, gradient descent translation machinery, which is basically the result of minimal eigenvalue of the Hessian not being too negative and the bound that is a result of the fundamental theorem, you immediately get a result for gradient descent. And the result is that gradient descent efficiently converges to global minimum almost surely under a random near 0 initialization. Okay, you get this for free just by analyzing gradient flow and feeding it to the generic translation machinery. Just a note about this result, to my knowledge, this is the first guarantee of gradient descent over a fixed size deep neural network. That means a model, a neural network whose size is independent of the data. Anyway, it's fixed, it's not the MTK regime, and the model is deep, that's 3 or more layers. And this is the first guarantee over such a model that gradient descent converges efficiently to global minimum almost surely under random near zero initialization. So there's several criteria that jointly, when they are required, this is the first result that I'm aware of that meets them all. And another thing to note is that we not only know that gradient descent converges to global minimum, but we actually know what path is taken to get there. The continuous analysis of gradient flow, we characterize the trajectories there. We can show which path gradient flow takes, and that immediately means that gradient descent takes the same path. And so characterizations of this form have the potential to not only shed light on optimization, but also on implicit regularization. It's not just about reaching a solution, it's which solution are you going to reach. Empirically, we show that over simple models and simple settings, indeed, it seems that gradient descent is not very far from its continuous limit. This is a result for MNIST. We just run plain vanilla gradient descent with a step size here, it's 10 to the minus 3, could be 10 to the minus 2 as well. This is a fully connected neural network with linear activation. And what we do is we run gradient descent with a baseline step size. And then we run it again with a step size that's 2 times smaller, and we compare every second iteration of this run to every first iteration of the original. So it's an apples to apples comparison. Then we run gradient descent with a step size that's 5 times smaller, compare it every 5th iteration, and we also do it with 10 times smaller and 20 times smaller. The left plot shows the training loss values over time. You can see that they're indistinguishable. On the right in blue, that's the distance of the baseline run from initialization against the distances between the runs themselves, and you can see that they're basically negligible. So in this setting, reducing the step size basically doesn't change the path at all. And this doesn't only happen with linear activation, it also happens with value activation, happens with convolutional networks. As long as the model is homogeneous, this happens. So it suggests that at least in simple settings, gradient descent is close to the continuous limit. A direction that we're looking at now is the large step size regime. So there's mounting evidence that using large step size is something that can be beneficial. It could lead to solutions that generalize better. And this is not something that gradient flow can explain. Okay? Because if gradient descent is close to gradient flow, it doesn't matter which step size you take in terms of where you're going to reach. It only matters in terms of how fast you get there. So if you reach solutions that generalize better, it means that you're outside the realm of gradient flow. However, there have been several recent variants of gradient flow that were suggested to capture gradient descent with large step size. And something that we're working on now is adapting the analysis to this case so that we can translate results from modified gradient flow to gradient descent with large step size. Let me just conclude. So the distance between gradient flow and gradient descent is small if the landscape along the gradient flow trajectory is roughly convex. That means that the minimal eigenvalue of the Hessian is not too negative. We saw that for deep neural networks that are homogeneous, have linear value or leaky value activation, this property holds. So the trajectories of gradient flow are indeed roughly convex. And we use this to translate an analysis of gradient flow to a result of gradient descent that is the first convergence guarantee of its kind. And empirically, we saw that, at least in simple settings, indeed it seems that gradient descent is close to the continuous limit to gradient flow. And just a hypothesis to close off with is that there are a lot of results, and there's a lot of literature on continuous dynamical systems, and specifically on gradient flow. And I really think that we've only scratched the surface in terms of the application of these tools to deep learning. And I really hope and believe that in the next few years, these tools, the continuous mathematical machinery that comes with gradient flow, will deepen our understanding of deep learning. So, thank you.
Thank you very much, Nadav. We have time for a question or two. So I have a question. You said that gradient flow trajectories are almost convex, even when the neural network itself is not convex. So can you explain what you mean by that? Some intuition behind that?
Okay. Yeah. Thanks. So it basically boils down to lower bounding the minimal eigenvalue of the Hessian. And what we can show, and what we do show, is that this minimal eigenvalue, there's something very special about gradient flow trajectories that start near zero. Because anywhere in space, this minimal eigenvalue is unbounded from below. It could go to minus infinity. However, if you start off near zero and you run gradient flow, there are different preservation laws, different symmetries that are preserved. And when these symmetries are preserved, the minimal eigenvalue is much, much larger. It's basically almost non-negative. And so this is something that we actually characterize and show for different kinds of models. It's a property that repeats itself for both fully connected and convolutional networks, and for both linear activation and ReLU activation. And this is kind of the source.
Okay, very interesting. I have a question from the audience. So, so your theorem about the global minimum, it applies also to nonlinear activations, not only to linear activations.
No, that theorem applies to linear. The machinery, the translation machinery, is general, but there is a caveat when you talk about nonlinear models. The caveat is that in nonlinear models, there's the result of the minimal eigenvalues of the Hessian, that those hold completely for nonlinear models. The fundamental theorem assumes differentiability. So for nonlinear models like ReLU, you get this kind of piecewise characterization, but you don't know what happens in the breakpoints with ReLU. And that's what we are missing to have a complete end-to-end result using.
So if you had nonlinear activation, but differentiable, it would hold.
But then the other result
like a sigmoid.
Yeah, but then the minimal yes, but then the result on the minimal Hessian eigenvalue, we don't have it for sigmoid. But so either you complete this side or this side, and then you get it for nonlinear.